weight, and we're going to start with this warp time issue here, okay? And this is what because people say, Bill, you're making fun of special relativity and general relativity.
You are by explaining.
Well, yeah, but
by telling.
I'm just saying what these people say. This is the explanation of why the Earth doesn't fly out of the solar system.
Australia must be having a bad time.
This is the physical mechanism that they propose. They say that the Earth doesn't fly out of the solar system because time is warped. And people say, well, that's not what they say. Here you see it. It's in front of your eyes. They're saying, look, Earth is encountering a wall, a warped time, and that's what prevents the Earth from flying out of the solar system.
That's just a metaphor.
And what they say, this is a metaphor. It's a figure of speech. You're not supposed to take it literally. Okay, if it's not, tell me what is. Don't say
literal?
What ain't. Tell me what is.
Yeah.
Okay, don't say that I got it wrong.
We can't conceive of it, is what they were saying.
Tell me what is the mechanism that relativity, special relativity, general relativity, quantum mechanics, string theory, I don't care. Tell me the mechanism mathematical physics proposes for why the Earth doesn't fly out of the solar system. I want a mechanism. Okay, and
not
you
a
say
description.
Right, don't tell me that time is warped. And then say, well, I didn't really mean that. You're not supposed to take it literally. No. If you're going to say time is warped, I'm going to take it literally. Whatever you tell me, I'm going to take it literally. So general relativity, at least, right, says that time is warped, and it means exactly that, literally. Time is warped because now you saw it here. Let me show it to you again. This is warp time. This is what it looks like. This is the mechanism that they propose. Okay? So the Earth doesn't fly out of the solar system because time is warped.
That makes no sense on so many levels.
Right.
Does time not happen above the net? Is time only on that
well,
net?
I mean, yeah, like you say,
where is time
you can take that to any level.
There's so many things wrong with it.
My point is that is the physical interpretation that relativity proposes for why the Earth doesn't fly out of the solar system.
But
you cannot say that's an analogy or you're not supposed to take it literally. No, that is the mechanism. If you don't believe that, tell me what the mechanism is that general relativity proposes for why the Earth doesn't fly out of the solar system. Don't tell me I'm wrong. Tell me what is.
Yeah, it's a simple question.
Okay? Very simple.
Answered.
And until you can tell me that, that is the mechanism. Warp time. They're treating time as a physical object, and they're curving it, and they're saying this wall of time comes up against the skin of the Earth, and that's why the Earth doesn't fly out. It's the roulette mechanism.
I feel the wall of time when I wake up early in the morning.
It doesn't squash it.
Oh, shit, man. How long am I going to sleep?
So the issue is that time, the time warpage and treating time as a physical object came out of special relativity, okay? And because of that, they applied it to mass, okay? And they applied it also to length, okay? Like we saw a minute ago. Okay, so what is it? Here we have this situation where a fellow says, no, it doesn't gain atoms, meaning, when mass travels at close to the speed of light, in special relativity, and I said, well, the reason special relativity or the explanation they give is that at high speeds, right,
things
gain weight,
mass or weight.
Well, that's the point. The point is, I'm saying it's one of the two. It either gains weight or gains mass. If it gains mass, if that's what special relativity says, it's acquiring more atoms.
Okay.
Because that's what mass is. It's defined as quantity of matter. Okay? If instead it presses on the scale harder because it's traveling faster and faster and faster, you have an acceleration against the scale, right?
That makes sense.
Then we're talking about weight and not about mass. So when they say mass increases, what they're saying is it's gaining more matter. That's what they're saying.
But that's the thing. They don't use their words.
No, but I'm getting to that. And here you can see when the mass increased, the mass of each atom is increased. This guy says the mass of each atom.
See, that's an incorrect way of using the word.
No, but then are they saying that
the atoms get fatter?
Get fatter, bigger?
That
more
means.
matter?
More matter. What?
But this is what this fellow says, okay? But then he contradicts himself. He says the weight effect at motion you mentioned is not related to the velocity, but acceleration. In other words, it speeds up, which is what I said the other day, but he didn't catch that. I didn't say it related to velocity. It's acceleration, just like gravitational acceleration. But he says special relativity theory is all about close to light speed and or supermassive scale. In other words, he's saying that the thing is he's saying two things. On the one hand, he's saying the atoms get fatter, and on the other one, he says it's traveling at bigger. It's accelerating.
The atoms get
So he's not telling us.
Why'd you put Beethoven there?
No, that's not Beethoven. That's what's his name? Newton. He's laughing at him. Newton is
so small.
No, but he's outraged by what this fellow is saying. You know. Okay, so here
the fat atom theory. You never heard the fat atom theory?
That's what it is. Okay, so here we have this. Oh, come on!
You need a better system to track things.
It just keeps falling on the other side sometimes. Okay, so this other fellow says mass, just as in Newtonian physics, refers to inertial mass, the ability to resist acceleration. No, that's not mass. That's called weight. Okay. So he says the fact that you interpret it as acquiring more atoms is just beating a straw man. You aren't impressing anyone. Mass is definitely not the amount of substance.
Okay.
That's what he's saying. Okay, listen to what he's saying. He's saying it's
so
not.
we all agree on that.
No, he agrees on it. He's the only person on the planet that agrees on that it's not the amount of substance.
I thought we agreed with that too.
No, mass is the amount.
Oh, mass.
Matter.
Sorry. Okay.
Yeah,
gotcha,
it's mass.
Gotcha.
For Einstein and the rest of the physicists, mass refers to the ability of an object to resist acceleration. And he puts the equation there. I didn't put that there, okay? He put it there. He says mass equals mass times acceleration. Force equals mass times acceleration. And essentially he's saying mass is equal to mass times acceleration, because he's saying that that's what mass is. Mass times acceleration. Yeah. Okay, so he's contradicting himself because he's saying mass is equal to mass times acceleration. He's treating mass as a force, and he's saying it's got to do with acceleration. That's what weight is, not what mass is, again. Yeah. And these people are cheating, and I'm going to show that more in a second. Okay, so please bear with me. I want to make sure we destroy this notion that mass is not the quantity of matter. Okay, so let's find out what mass is. Here we have the Wikipedia and the dictionary, two independent sources, and they put them under physics in both cases, math phys, not physics, but the force acting on an object due to the acceleration of or gravity, which is weight. That's the definition of weight, right? The force that gravitation exerts upon a body equal to the mass of the body times the local acceleration of gravity. Okay, a measure of mass. That's what weight is. It's a force. Okay, or at least this is what we're going to challenge that as well. It's not a force, but that's what math says. Math phys. Okay, mathematical physics says weight is a force which is equal to mass times acceleration. So these people, when they say, look, it's the inertia, the ability to resist change, they're talking about weight. They're not talking about mass. Mass is the quantity of matter, as we will see in a second here. So let's first show this. Let's prove the definition of weight and mass. Okay, here's a distinction between weight and mass. Here we have NASA. Okay, it says, what is weight? And it says weight is a force, right? Force equals mass times acceleration, right? Caused by the gravitational attraction of the Earth. And here's the equation of weight, okay? This is what I want to show. Okay, this is the weight equation. It says force equals gravitational constant, mass 1 times mass 2 divided by distance squared. And eventually they end up with weight equals what? Mass times acceleration of gravity. The little g is that with gravitational acceleration. So that is weight, which is, according to mathematical physics, a force. Okay, so again, what you have to look at is that these are the definitions that mathematical physics has out there. Okay, you cannot say later on that you're going to change all this and and give your own definition, like these people are doing. These people are saying, well, no, that's not what it is in relativity. No, mass is mass and weight is weight.
You can give your own definition.
Yeah,
as long as
you
they make
can,
sense.
but then you got to continue. You cannot say that for this I'm going to use this notion of mass. For that I'm going to use another notion of mass, because then you're using word salad. You're doing semantics. Okay. They always accuse me of doing oh, he's got semantical arguments. Well, now you're doing semantics if you're going to change the definitions on us. Mass, quantity of matter, weight, mass times acceleration. In other words, the something pushing up against a scale.
Yeah.
Inertia, that's weight. That's not mass. Okay, inertia is not mass. Okay. And let's make sure we understand that here. See what this says. Fellow says the theory of relativity has been proved. See, they always prove all these things, right? Correct in the past by equipping synchronized atomic clocks to 2 different satellites, okay? Furthermore, modern GPS, in order to work, takes time dilation into consideration. We are absolutely sure that the flow of time is relative and its flow is not a constant. There are no doubts about it. Again, what these people are talking about always is that special relativity for time dilation, weight, mass increase, and length contraction have been proven. Okay, they always talk about proof, about truth. They say, we know it's a fact. Okay, and so you can't even talk to these people because, they already proven everything. Okay, but getting back to mass here, we have definition of mass. Okay, says, Museum of Natural History says, mass and weight may seem to be the same thing, but in fact these 2 measurements are very different. What is mass? Mass is the total amount of matter or stuff in an object. Very clear? Weight is the force of gravity on an object. Okay? Mass always stays the same, but weight can change depending on how much gravity is acting upon an object.
I think that says it pretty concisely.
Yeah, I think it's clear, right? Yeah. And here we have...
I think we got it, Pops. You're going crazy on this guy.
Yeah, here Wikipedia says something similar. Okay, it says... In scientific concept, mass is the amount of matter, right, in an object. Weight is the force exerted on an object matter by gravity. So I don't know what all these people don't understand when the definitions are out there and they say, well, no, mass is what Einstein said for special relativity, which is that mass is the amount of inertia. Okay, and here we have some people who say that, and these people, again, you wonder about them. Here's one way they always prove to you, okay, that mass is always the same, but what changes is weight. And I think everybody learned this in high school, okay, or thereabouts. You take the 1 kilogram, right, and you take it to the moon. Does it weigh 1 kilogram? And they say, well, the mass remained the same, but what changed is the weight. Standard, high school stuff. And you say, why did the weight change? Well, because the gravitational attraction changed on the moon. There's less gravity on the moon. Why did the mass stay the same? Because the number of atoms, the quantity of matter, is the same. Okay, so we got that. Mass never changes because it's the quantity of atoms. Quantity of atoms, we count. We count how many atoms. Weight, we measure. Measuring and counting are 2 different things.
What about the fatness of the atoms? Have we put this into consideration?
Well, the fatness of the atom, let's assume that. I mean, what are we saying now? How did it acquire more? How did it become bigger, the atom? Acquire more matter, right? Because, I mean, how else are you going to explain it? So whatever little bits of matter came into it, that's how the atom became fatter. You can't escape mass being the quantity of matter. Anyone who changes that definition is lying, is simply trying to get his theory through at all costs, trying to win an argument. That's all. Ignorant. And that's what the special relativists did. They simply wanted to win an argument. That's it. Nothing more than that. Because they had to change the definition in order to tell you that mass changed. When everybody says mass cannot change because you count mass. How many marbles are in the bag? There's 10. There's always 10 unless you had more marbles in there.
Where'd the 12th marble come from?
Right. That's it. You got to put more marbles if you want to have more mass inside the bag. if the bag travels and goes faster and faster to this acceleration and presses down on the scale stronger and stronger as time goes by, then you have weight.
It can act as if there were 12 marbles.
Right, and what is the scale doing? That's the inertia. That's the inertia part of weight. Okay, yeah. So don't tell me that's got either one of those has anything to do with mass. Yeah. Mass is the quantity of matter. It never changes. Okay, and so for people to say, well, no, we have another definition of mass, and here we have it. In fact, someone tells you why they came up with this mass changing in special relativity, and this is from the University of Virginia. So this is their explanation. Okay,
mass really does increase with speed.
Yeah, mass really does increase with speed, but then he goes in there with a caveat. He says, actually, there is continuing debate among physicists, meaning mathematical physicists, they're mathematicians, they have nothing to do with physics, concerning this concept of relativistic mass.
Relativistic mass?
Yeah, it says the debate is largely what? Semantic. Yeah, and here you can see why it's semantic, okay? Give me a second here.
It's just a bunch of miscommunication.
No, here it is, look. Here's the Wikipedia, shows you why it's semantic. In physical science, meaning in the religion of mathematics, right, one may distinguish conceptually between at least 7 different aspects of mass, or 7 physical notions that involve the concept mass. Okay, you can see where the problem starts. Yeah, if you have 10 different definitions for mass or notions, then we're all going to run into trouble. Okay.
And then people wonder why you're so anal retentive about
definitions. By definition and language. And here's what John Wheeler and Edwin Taylor said in their book, Space-Time Physics, says, nature does not offer us any concept as the amount of matter. History has struck down every proposal to define such a term. Even if we could count number of atoms or by any other counting method try to evaluate amount of matter, that number would not equal mass.
What does he mean by that number would not equal mass?
Well, the issue here, again, is that all these people cannot define mass. They cannot define mass.
Hold on. But that last line I thought that is mass. If you count the number of atoms.
But because they're trying to say,
why? What I mean is, why? Hold on. Why would that not be a sufficient?
Because they need to change it to explain space-time physics, which is the name of their book. They cannot talk about space-time if mass is the quantity of matter. That's the whole issue. Okay, so they had to cheat.
They had to put in that's why he put that last line is a lie to fit his stuff in.
Right, and that's
what's saying. Even if you could count them, there's some magic there.
Yeah, they have to stop defining the word mass. Because if they define the word mass,
it's in the way.
If they define the word mass very stringently, very strictly.
Yeah.
Not with 10 different definitions, 7 definitions. If they have only one definition for mass, they're dead. They're dead because either it's quantity of matter or it's inertia or weight. And what these people, they want to put the weight in there, but they want to call it mass.
Yeah.
That's the problem. That's the whole problem.
Jesus.
It's a semantic issue, like this guy said. Okay, and so here.
That's so crazy.
Says, so how can this mass increase be understood? Yeah, how can it be understood?
It depends on what the question was.
No, it depends on how you define the words, Every form of energy possesses inertia. Huh? What's this got to do with mass? The kinetic energy itself has inertia. Okay, and it says inertia is a defining property of mass. Okay, let's find out what this inertia nonsense is. Okay, it says inertia is the idea that an object will continue its current motion until some force causes its speed or direction to change. Okay, so again, we're talking about resistance. That's what inertia essentially comes down to. And we have Don Lincoln over there at the Fermi Lab, and he says at low speeds, inertia equals mass. At high speeds, inertia does not equal mass. So these people are playing around with words. That's all they're doing. Like it says there, the debate is largely about semantic. Okay, largely semantics. And it says the increase in kinetic energy, E, over the 1 second period is just the work done by the force. Okay, so they're talking about, again, force equals mass times acceleration. They're not talking about mass. Okay, that's the whole issue. And here you have what it is. Here's a picture of that. We have the little atom. It's pressing down harder against the scale because it's accelerating. That's what's called inertia. Inertia has to do with weight and not with mass. Force, according to mathematical physics, is equal to mass times acceleration. What they've done is they've replaced the word force with mass, and they replaced the word mass with inertia, essentially. You know, they're saying, well, we're not really talking about mass. We're talking about inertia. At high speeds, mass is not equal to inertia. Okay, so all they did was play around with words throughout.
Well, one problem that definitely comes along with mass
Uh-huh.
is what one of our people here pointed out, that even if you could count an atom, a hydrogen atom isn't the same as a uranium atom, and they have different masses.
Yeah, but that's why
I mean is it's hard to quantify in that sense.
It ain't.
Why not?
Like I say in my book, the unit of mass is the hydrogen atom. What is a uranium atom? It's 92 hydrogen atoms. That's all they are. So we use the unit of mass always as the hydrogen atom. Why? Because from every hydrogen atom, we have a single rope connected to every atom in the universe. What does that mean for uranium? Uranium has 92 atoms, right? Hydrogen atoms, there's 92 ropes, one for each one of those atoms connected to every atom in the universe. It's very simple, okay, to understand. It's a conceptually straightforward. Okay,
well, I guess it would be hard to determine, because how do you count the hydrogen atoms?
It's an assumption.
Uranium?
It's an assumption. All these are assumptions. Okay, you have to begin with an assumption in order to explain your theories. That's the assumption. The assumption is every hydrogen atom is a unit of mass. Everyone has a single rope connected to any other hydrogen atom in the universe. Straightforward. If one atom is big, like
a fat
atom. We have 92 hydrogen atoms stuck in there, compressed by what? By the sun. That's how we made it, a star, right? Okay, so where does this take us? Well, what we do in science is we try to define the words, especially try to figure out the difference between force and tension. Weight is not a force, as mathematical physics has held since the days of Newton.
You have to go slow with this one, man.
Yeah. So let's
weight is not a force.
Yeah, let's put our universal movie thing here. What is the universal movie? It's a snapshot of everything in the universe at a given location. Like if we froze the universe, right? You take a snapshot. Now everything moves. Whatever tiny amount moves to the next location, you take another snapshot, and everything moves to another location, take another snapshot. So we have the movie of all these snapshots. In a snapshot, all you see is what exists, all that, the atoms in the universe, where they are, etc.
There's no motion.
There's no motion. Yeah. Okay, and so anything that's in a single frame of this movie is static. It only represents static concepts, and here we have them. Okay, object, distance, location, and existence fit in a single frame of the universal movie.
And you use this as a tool. To separate that which exists and that which doesn't.
Essentially, but not only that, it defines certain concepts that can only fit in a single frame. In other words, that are static concepts versus dynamic concepts, which require at least two frames or more of the universal movie. And that's why we separate these static single frame concepts from dynamic concepts, which require at least two frames. That's the notion. Okay, and people have a hard time understanding the difference between static and dynamic concepts. That's what this tool is used for. Motion requires two frames of the movie. You cannot have motion in a single frame of the movie. The Mona Lisa doesn't smile in a single frame. If you want her to smile, you need to see at least two frames of Mona Lisa. Okay, smile is a verb. Okay,
you're saying she's not smiling.
She's not smiling. No.
Oh shit! You're blowing my mind on too many levels now.
Okay,
so Mona Lisa's not smiling.
Okay, but here's the issue. The issue is you have all these static concepts: object, distance, location, existence. All are static concepts. You do not need to move in order to exist. You can't move if you have location. If you move, you have motion, not location.
Let me just bring back the original thing. The reason you brought this up was because you're trying to explain.
Differentiate or separate static concepts from dynamic concepts. Love is a dynamic concept. You cannot put love in a single frame of the universal movie.
No, earlier than that. Well, the reason you brought this up is because you're talking about tension versus force.
Yeah, here it is, and I've got them there. So we have tension is a static concept. And the mathematicians have turned it into dynamic concept because they say tension is a type of force. And the way they explain it, and here's a graphic version of it so that you can see how mathematical physics has screwed this one up completely. Here we have it. They say tension, on the right side there, is a string that's being pulled from two sides. It's pulled by the box, which is being pulled by whatever gravity is, downwards. And at the same time, it's pulled by the roof or the ceiling or whatever where the string is tied. So what they say is you need two forces, two dynamic concepts to produce tension.
Two counterbalanced ones.
Yeah, but tension is a static concept because there is no motion once something is completely tense. And this is where the problem is because they've defined tension as two forces in opposite directions.
Two motions.
Whereas we define tension as a static concept because nothing moves. It finally reached a equilibrium where nothing moves in the string. The string is stretched to maximum. Okay, so tension is not a force. And that's the first issue that we want to put through. And so we're going to replace the word force in mass divided by distance squared in Newton's equation. We're going to omit the g there, the gravitational constant. Weight equal to mass distance squared is not a force, it's a tension. Okay, that's what we're going to argue here. Okay, tension is not a force. Why? Because force and influence that causes the motion. The motion. There is no motion in tension, but there is motion, hopefully, in force. Someone wins the tug of war, okay, of an object. Tension, acceleration is zero. The system is in equilibrium. A system is in equilibrium when the sum of all forces is zero. So that's a definition that comes out of Wikipedia, but the point here is that if it's in equilibrium, it becomes a static concept.
I would say the difficult part to understand this is you don't make force an object as most people do. Because force in the mind of people, like when you have the pendulum, what's it called? The Newton's cradle, right?
Yeah.
When someone said, when a little kid asks, how did the first ball cause the last one to fly off?
Yeah.
Normal people would say, the force traveled through these and hit it away.
Yeah, the energy.
The energy.
The energy, the field.
But you're not making that step. You're not saying you're not objectifying energy or force. And that's the part that's hard to understand with this.
Yeah, because people turn everything into physical objects. They say energy is a physical object.
That's what I'm
saying. Force
saying.
is a physical object.
I have a buddy.
Field is a physical object.
I have a buddy who's an engineer, and he also talks about forces.
But
he talks about forces with tension. Like he'll say the force goes through here and here.
Yeah,
and it's
goes.
But there is nothing traveling.
No, but the
There's
question
no one
is,
winning the tug of war.
Yeah, but the issue here is that they use the word force, but they use it as a physical object in a physical interpretation. In physics, that's a no-no. That's unscientific.
When I'm pressing my hands together, they say, there's two forces that are going towards each other, and you would say no.
No, because force cannot go through anything. Force is a concept. You cannot say force does this and force does that.
That's the hard part.
What you got to tell me is what physical object does this, causes the force.
That's the hard part.
And that's where people never get into. They say the force does it.
When a billiard ball hits into another one, someone will say, okay, where did the energy go?
Yeah.
Where did the motion go? And you're like, there's no such thing as something as a motion going somewhere.
Right.
There's no such thing as energy going anywhere.
Energy, force, field, those are not physical objects. You cannot use those in physics.
But that's really hard to wrap your head around.
Those words has been brainwashed in high school.
But it's not just brainwashed in high school because as we see it, it feels like a physical object. When you see a ball roll at one, hit one, and then this one goes on, this one stops, you're like, something got transferred. It just looks like that.
An object is not that which you can see or touch.
I know.
An object is that which has shape.
Okay, robot, beep boop, fuck.
I'm the IA.
Yeah, you're like, but it's hard to wrap your head around that part.
Okay, so
when you say a force is only when a tug of war is won, that is a thing that most people would have trouble with.
Yeah.
Because people would say even if no one's winning the tug of war, there's forces, there's strengths at combat there.
Yeah, but strength requires an object. Otherwise, you're doing black magic. You're introducing spirits.
Yeah, but that's how they speak of it when they say
I know.
there's a lot of forces
Because
in this room
everybody's been
that we can't.
brainwashed in high school
No,
to treat
but
these words as objects, as things.
but like if you ask anyone, they'd be like, okay, there's a lot of forces in this room that we're not aware of. Like for example, there's a million forces. I'm just talking about not physical. I'm not speaking scientifically right now. I'm speaking in normal talk. There's a lot of forces in this building.
You said it.
That's the key issue. A normal speak, common speak. In fact, I'm sure architects even speak like this. When a building is being constructed, they have to calculate where all the forces go.
Yeah, but
whatever that means.
Yeah, but then
and it's a tug of war. No one's winning the thing, or else the building would fall apart. Obviously,
but that's why we need to do semantics, word salad. We have to do what does the word force mean? Look up the definition, and it says something about motion, and a verb, motion, is a verb. So you cannot say the verb did this, the motion did this.
Yeah, the motion is moving.
Right, that's what you're saying. So you cannot use the word force in science. The word force is outlawed. The word energy is outlawed.
But then it becomes
all these
hard.
Words,
but it becomes hard to speak without. That's what I was telling you. When it becomes hard to speak without a metaphor, because even if you define it, you still have to use words to talk about the forces going through the building.
That's why you have to identify the physical objects that are invisible, intangible. That which we can see or touch is not an object. That which has shape is an object. So you have to draw the object that you're proposing. You cannot say the force does this, the field does that, the energies does this. That's irrational.
Yeah.
Time does this. Time doesn't do anything.
It's hard not to objectify energy. Because,
and that's the problem. All these people are talking with concepts.
But the basic example is the two billiard balls hitting each other. There's the same amount of mass. There's no mass is being added or gained or transferred, right? It's just motion of one hitting the other, and then the motion being transferred. But obviously, since motion isn't a physical object, it can't be transferred.
Right.
But something is moving or something's happening.
That means we don't understand what causes Newton's cradle until you identify all the invisible stuff in the room.
But it's not even invisible. It's just not there.
Well, no, because
it's something happening.
No, because if you explain it saying that what was transferred was the force, what was transferred was the energy.
You didn't explain anything.
You haven't explained it.
Yeah. Okay. I'll grant you that. But how do you speak in terms when it isn't an object?
We always have to use objects.
So we can all agree there's no object. There
are objects.
We have a ball and you have another ball. But the third thing that we turn into an object that isn't an object, the energy.
That's for the next class.
It's such a simple happening, but it's like a spirit.
Okay, so let's end this with this. Here is our solution to this. What is mass times mass divided by distance squared? Well, mass divided by distance squared is the number of ropes that interconnect two objects at a given distance, and we're isolating all these two objects here from all other objects in the universe, which is not completely true. It's just so that we understand the concept. So what is an effective rope? Well, we say that if you have atoms 1, 2, 3, 4, and 5 of the cube there on the same line, on the same axis as number 6, that is an atom of the cylinder, okay? You have only one effective rope. It's like number 1 is pulling on number 6, and that's it. And 2, 3, 4, and 5 are irrelevant. You can prove this to yourself with a rubber band, okay? You just take a rubber band and 3 fingers, and in fact, we can do it here. Let me show you here. Give me a second here. Maybe we can do it here. No.
Oh. Experiments. I thought we don't do these.
Well, this is not an experiment. This is just this is not an experiment, okay? Because people say, "Oh, Bill, you did an experiment. You did it on Sunday." No. This is not an experiment. What we're doing here is we're going to show you something so that you understand the concept, okay?
You need a new rubber band.
Well, no, but this is the point. The point is, if you just hold onto this, okay, a third person, right, holds onto this. All you have is the tug of war between my hand and his hand. I don't feel at all any tug. You want to feel a tug, you got to pull it out of alignment. Now you feel a tug.
Do it down so they can see it.
Okay, well, pull it all
If
over.
you pull it towards them, they won't see it.
Okay,
So this,
so
this I
now,
can feel the tug. Here I can't feel the tug.
right.
Okay.
So you want to see how mass appears and disappears? There you have it. Mass appears, mass disappears.
Oh, don't say it like that. That's confusing.
See?
You
Why?
mean the illusion of mass?
Well, you feel a different force. There's
Yeah.
something else in there that suddenly
yeah.
you don't feel it when they're on the same axis. You do feel it when they're not. Okay, and that's what we're showing here. Okay, again, no experiments. That wasn't an experiment. Okay, for those who that the purpose of that was a demonstration just to show you the concept. Okay, and so what we're saying is if all atoms are aligned, you only have tug of war between number 6 and 1. If you want to feel atoms 2, 3, 4, and 5, you got to move the cylinder closer to the cube, and then you can see the ropes go out of alignment. They're not on the same axis. Now you feel atoms 2, 3, 4, and 5. What has changed? What has changed is a number of effective ropes. Okay, and that's what gravitational attraction is, the acceleration of gravity. And there you see it on the upper left, right. Two atoms or two objects there, a cylinder and a box. They're very far away from each other. All the ropes are almost on the same axis. So gravity is very, very weak. As the cylinder and the box, the cube there, approach each other, you can see what's happening to the ropes. They fan out, and very close together, they fan out even more. So we have more and more effective ropes. That is the acceleration of gravity. That's what mass 1, mass 2 over distance squared represents. It's the number of ropes that interconnect the atoms of these two objects. Okay, so it has nothing to do with really with what these people say, which is inertia.
I mean, I would go. I still think you're not giving it full credit because I don't think it's just effective ropes when the ropes are superposed on top of each other. I think it's the aggregate of the angles. Like,
well, it's the same thing. It's
the same thing.
It's the same thing.
But you're making it because you're making it binary. They're either on top of each other or they're not. But this is different than that also.
Yeah, but the point here is the following: you have the Earth and the Sun. They're very far away from each other. Yeah. If you take the Earth and take it all the way to Alpha Centauri, 4.3 light years away,
a lot of those will overlap.
They'll overlap more and more and more, all those atoms. So the gravity will be very, very weak. But as soon as the Earth comes closer and closer to the Sun, those same ropes will tend to separate, not be on the same axis, and now you're going to feel gravitational attraction. Imagine if the Earth were close to where Mercury is. Well, you can see why Mercury is being whirled around so differently. Why the perihelion shifts so much, because take a little bead, move it around your finger, and you'll find out it goes in all directions. Now you take that string, make it long and put a bowling ball and you twirl it around and it'll be very smooth. And that's what's happening in our solar system. That's the reason for the perihelion shift of Mercury. You're just the sun is twirling around a little bead very close to it, and all the ropes are not on the same axis. And when you have a long string, like, I don't know, a bowling ball far away from you and you swing it around, well, then now even if you had every atom tied to your hand, it's far away, they're almost all on the same axis. That's the difference between the Earth, for example, and the weird motion of Mercury. Okay, I think we beat this one to death. Obviously, there's a lot of questions on this issue. Okay, so all we can do is present in general terms what we're talking about here so that people get the general notions.